So for our Capstone design, we designed a direct digital synthesis controlled pure sine wave converter. Our group consists of me, Nabil, Ian, Damon, and Kunal. So traditionally, we use analog signal conditioning processes to generate the SPWM signals, but for our design, we want to do them all digitally. So our Arduino sends out these SPWM control signals into the H-bridge, which consists of gate drivers, and out of the H driver, we'll get our SPWM signal that's gonna have a 0 offset, and it will be our AC signal that's gonna go into the transformer. And to provide the power to the MOSFETs, we have to use a DC to DC converter to take the 12 volts in, convert it to 21 to serve as a DC bus. Then once it goes through the transformer, it gets stepped up to 170 volts peak to peak or 120 RMS.
We had several hardware-related research challenges that we had to account for during our project. One was compensating for shoot-through current, which occurs when a pair of series MOSFETs, which you can see in the H-bridge right here, they conduct at the same time, thus shorting the DC bus to ground. So we were able to model this in PSpice, as you can see in this schematic over here, and we generated the PWM signals using analog components, but these were just models of the Arduino. And we were able to find that the IR2103 gate driver worked the best and prevented the shorting problem.
So our inverter uses DDS, or direct digital synthesis, and this DDS was implemented using a microcontroller, and we had two choices. We had to choose between MSP430 or Arduino, and we had our sine wave working with both the MSP and the Arduino, but we went with the Arduino in our final project because the MSP we were encountering interrupt issues and the programming and implementation of the rest of our circuit. So we made sure to use Arduino in order to have a better operating environment and a better operation of the whole circuit in totality.
Now the way DDS works is you have a sine lookup table and you basically calculate the tuning word, and the tuning word depends on your desired output frequency. So for example, if the tuning word is 1, you go through your sine lookup table like through each sample. If the tuning word is 2, you go through like twice as faster. So your output frequency will be twice as fast. So that's basically how DDS works, and that's how we generate the SPWM signal.
And the tuning word basically governs how fast or how slow the phase accumulator goes to the sine lookup table, and that ultimately governs the overall frequency that the system chooses.
So this is the final design of our project. This is the whole H-bridge and the transformer and the output caps. This serves as our boost converter serves as the DC bus. And this is the Arduino that sends the control signals. And here's the switch that turns on our system. And here we get a 121 volt RMS at 60 Hertz, as expected.
Good for you.